We now move to chapter 2. This is a chapter on vehicle dynamics. Essentially, how does a vehicle move? What are the forces that act on it? What speed does it move? How does it climb a hill? What is the energy that it consumes? What is the power that it consumes at every instant of time? This chapter is common for a petrol vehicle or electric vehicle or vehicle powered by any kinds of energy. Essentially an interplay between forces, energy, power, and we will understand this. The first important thing that we like to understand at any point of time, whether it is a flat road or a slope road, any kind of road, how much power is required to drive the vehicle at that instant. Power is always at a particular instant. It keeps changing from second to second. How much power is required over the last 1 second or next 1 second. And then an important thing is how much energy is required. What is the total amount of, if I go from one place to another, what is the total amount of energy that is consumed? Now, why is power important? Why is energy important? Power is important because my motor and controller in electric vehicle cases, my engine, IC engine in petrol and diesel vehicles must give me that power. And if it is not capable of giving me that power, what I required instantaneous power, well, it does not satisfy my need. Why is energy required? Energy is related to the fuel consumed, whether it is a petrol or diesel or electric vehicle, how much electricity is consumed, how much of my battery will get emptied in the process. So, how much energy is required is equally important. All vehicles have a maximum power, beyond that it will not be able to provide a power. It has a maximum energy, the maximum energy is determined in a petrol vehicle by size of the fuel tank, in a electric vehicle by amount of electricity that can be stored in a battery and used before you need to recharge. So, that is the reason power and energy is always important. Power is instantaneous, energy is over a particular road trip. Of course, to answer this question you need to know several things about the parameter of the vehicle. First is what is the composite mass of the vehicle including passenger and goods, the gross vehicle weight, because if it is moving with more people, more goods or a heavier vehicle, it will take more power and therefore more energy. If the vehicle weight is less including the passengers, then it takes less energy. This is obvious. The second very important thing is what is the condition of the road. Now, we are using wheels. Is there can the wheel move very easily, or the wheel itself while it moves, does it consume lot of energy, lot of power? It is called rolling resistance. For example, if it is a rough road, it will consume more power. A smoother road will consume less power, but there is a minimum friction required, otherwise we will slip. You do not want slip. So, rolling resistance is an important parameter that we will discuss in this course. The third force that we need to worry about, one was the weight of the vehicle and this results into various forces, the rolling resistance. The third is the aerodynamic resistance. As the vehicle is moving, certain amount of air it is displacing. Now, depending on the amount of air it is displacing, a certain amount of power will be required, certain amount of energy will be required, and that is called aerodynamic drag. It tries to, the air tries to stop the vehicle and you need to overcome that by a certain force. Is there an incline? Are we climbing up? If we are climbing up, obviously we are working against a potential energy, and to that extent a certain amount of power and energy will be required, and that is referred to gradient resistance. Now remember, if you are climbing down, in fact you are gaining potential energy. So in fact you can gain the energy. We will talk about both this and what is called that when you go to the vehicle down or decelerate with the vehicle, you can recover part of the energy and feed it back to the battery. Particularly very important for electric vehicles, not as important for petrol powered vehicle, because you cannot cannot convert energy back to petrol. Petrol will be consumed once you accelerate or climb up. There is yet new concept that we will bring, that suppose you take a full road trip, the vehicle is accelerating, decelerating, climbing up, climbing down at different point of time. Each trip in some sense is different. Then how do you compare one vehicle to another? For comparing one vehicle with another, you define a standard drive cycle, saying for so many seconds you move at this speed, for so many seconds you accelerate, so many seconds you decelerate, so many seconds you move at another speed, so many seconds you climb up, so many seconds you climb down. Now this is in the full drive from one place to another, this traveling at different speed, accelerating, decelerating, climbing up, climbing down, all these things can be recorded. This drive cycle is standardized so that you can compare one vehicle with the other, and we will introduce the concept of drive cycle and discuss more about it. There is a final parameter that becomes important. What is the maximum speed at which the vehicle can go, because your engine or motors cannot go beyond that speed. What is the maximum speed, and what is the maximum acceleration that it in so many seconds you want to go from 0 to so many kilometer per hour. What is the maximum acceleration for the vehicle? These are the important parameters that we are going to look upon it. So here is the same thing, I am diagrammatically representing that. I am showing the vehicle is climbing up at an inclination of theta. Now of course I can make this theta to be 0, in which case it is going flat, or theta to be negative, in which case it is climbing down. So the weight mg of the vehicle, it has a component which is vertical to the road, perpendicular to the road is mg cos theta. It is one which is horizontal to the road, which is in the same direction of the road, is mg sin theta. Mg sin theta is going to be the force acting when you are doing rolling resistance, and mg cos theta is when you talk about the total weight of the vehicle, and then there is aerodynamic resistance and rolling resistance. And as I told you, there are 4 forces that we need to overcome: aerodynamic drag, rolling resistance, uphill resistance, and acceleration. Okay. Aerodynamic drag, you displace a certain amount of air. This is given by half into rho. Now what is rho? Rho is the air density, and at 27 degrees centigrade the density of air mostly is 1.2 kg per meter cube. You can take that as a standard, but at some places depending on the height at which you travel, rho may be different. So therefore you may have less or more drag. There is something called drag coefficient. Now the drag coefficient will depend on the way the vehicle is designed. So you are going to get a drag coefficient. If the vehicle has smoothness, it will have lesser drag coefficient. If the vehicle is like flat and something like that, it is displacing air, the drag coefficient will be more. And then the frontal area, how much air are you moving? So it is half into rho into CD into the frontal area multiplied by V square. This is the aerodynamic drag, V square. This is the force, aerodynamic force that is acting on the vehicle, and it goes up by velocity square. So, if you are driving at 30 km per hour, you get certain aerodynamic drag. You go to 60, your aerodynamic drag force required goes up by 4, not by 2 times. Very, very important. And we will show you the energy required goes up by V cube. This is something that is important that for us to understand. We use standard standard terms here. Velocity is always given, units are meters per second, air density is at 27 degrees centigrade or whatever degree centigrade is given as 1.2 kilogram per meter cube. Area, frontal area, projected area is given in square meter, and the drag coefficient does not have any units. So, you need to take that, you can calculate therefore, what is going to be the aerodynamic drag force. The second is this inclination. There is a term that is defined. First is a gradient in percentage. Generally, you take height of the grade, which is p in this case, and base of the gradient, which is b. So, p by b into 100% is called gradient in percentage, p by b into 100%, that is a gradient in percentage. But very often gradient is also given in degrees, in which case it is a tan inverse p by v. Now, this is a very important thing, because people either specify in terms of percentage 8% or 12% or sometime in degrees, and you need to just be able to compute this. So, that gradient plays an important role, and gradient will vary. If you are climbing up, for example, today the gradient is maximum, of course, on hilly road there is always gradient, but also on certain overbridge you get gradients, you get gradient in parking lots a lot. So, you need to take that into account. Then the rolling resistance, basically the tires when they rotate, certain resistance mg cos theta, mu in mg into mu cos theta. Mg is a mass into gravity, mu is the rolling coefficient, and the rolling coefficient will depend on the kind of road that you have. And mg cos theta, well, if theta is 0 degree, then cos theta is 1. So, mg mu, this is the rolling resistance, this is the force that is acting on rolling resistance, trying to, and its force which is always acting against the direction in which vehicle is moving, and therefore, it is going to try to slow down the vehicle. You need to overcome this force to be able to move the vehicle. And mass is of course in kg, weight is in terms of mg Newton or kg meter per second square, where g is the standard 9.80665 meter per second square, and mu, the rolling coefficient, is again a coefficient which has no units. And as I pointed out, uphill resistance or climbing force is mg sin theta, that is the uphill resistance mg sin theta, where theta is a maximum grade, theta is in degrees, or you can convert theta into pi by 180 degrees radians. So, then you can just actually do that. So, these are the 4 forces. One is a gradient, well 3, gradient, rolling resistance and aerodynamic, and whatever your engine is or motor is has to overcome all these 3 resistances or forces for it to start moving at a constant speed. And then you may want to accelerate. If you want to accelerate, then you require the force required for acceleration, and force required for acceleration is force equal to m into a. Before we get into acceleration, let us do a very simple assignment, and part of this assignment I will solve so that you can get used to it. This is the assignment 2.1. it basically says compute forces due to drag, rolling resistance and gradient for the following vehicles. There are 3 vehicles, one 2-wheeler, 3-wheeler and 4-wheeler, and we want you to compute the force due to drag, due to rolling resistance and due to the gradient. We are assuming rho equal to 1.2 kilogram per meter cube, more or less use that as a standard. In this case theta is taken as 8 degrees. So, there is a gradient of 8 degrees. For the 3 vehicles, 2-wheeler, 3-wheeler and 4-wheeler, and we want you to compute this at 2 different velocity v1 and v2. So, find the rolling resistances of the at 2 velocities, find the aerodynamic drag at the 2 velocities, and finally find the also the gradient resistance. We have taken this 2-wheeler, we have taken gross vehicle weight to be 200 kg with passenger. We have taken CD to be 0.9, the coefficient due to drag, and frontal area is 0.6 and the rolling resistance mu as taken as 0.015, and the 2 velocities that we are choosing is 30 and 80 kilometer, and tire radius is important, meters is 0.28 meter. 3-wheeler has a smaller tire, 0.2 meters, weight is much larger, 600 kg. Coefficient of drag is 0.45, area, frontal area for 3-wheeler is larger, 1.6 square meter, mu rolling resistance is same, rolling coefficient. 4-wheeler on the same road, weight is much larger, 1500 kg, drag coefficient is 0.3. Remember that this is designed to have a lower drag, area is of course larger, 2.5, the rolling resistance is same, and the 2 velocities 30 kilometer per hour and 80 kilometer hour, and tire radius is 0.3. Now, in these 3 cases you are supposed to compute, and I will do only one of these computation for you to try to get you to get a good feel. So, first only for A, for part A, that is the 2-wheeler, I think I am doing the calculation. So, the drag in newtons is half into rho into CD into area into velocity square. Now, rho is 1.2, half is 0.5, rho is 1.2 kg per meter square, area per meter square, area is given, and CD is also given, and velocity square in meter per second square. So, this comes 0.5 into 1.2 into 0.6 is the area, and 0.9, oh, is it 0.6 or 0.9 is the area? 0.6 is the area and 0.9 is the drag coefficient. Velocity is 30 kilometer per hour. You have to convert it into meter per second. To convert it into meter per second, kilometer to meter is multiplied by 1000, so it becomes 30,000. But kilometer per hour was there, so you have to divide by 3600 to get meter per second, and you have to take the square of that, and that you compute, and it comes to 22.5 newtons. This is at the velocity of 30 kilometer. You can do it for 80 kilometer also. Okay. What about the drag at 80 kilometer? Instead of 30, it becomes 80. And so, it is 8 by 3 square, velocity only changes, nothing else changes, and from 22.5 Newton it goes to 160 Newton. Why? Almost 8 times, 7 times. Why? From 30 to 8 t, you have gone 8 by 3, but it is a square of that matters, and that is the reason the at higher velocity drag can becomes very, very bad. What about rolling resistance? Rolling resistance is mg mu cos theta, mass is same 200 kg, g is 9.81 meter per second square, mu is 0.015, that is what we had chosen, 0.015, and cos theta is cos theta, theta is 8 degrees. So, 8 pi by 180, pi by 180. Okay. With that you do the computation, cos 8 pi by 180 is approximately 0.99. So, the rolling resistance does not make much of a difference, whether it is a flat, it would have been cos 0 or cos 8 by 8 degrees, it does not really make a difference. So, you get 29.4 newtons, more or less similar to what you would have got on a flat ground, very small difference. If you look at it, rolling resistance is larger than the drag, but much smaller than the drag at 80 kilometer per hour. At 30 kilometer per hour, it is larger. Climbing force is mg sin theta, again m is 200, g is 9.81, theta is sin 8 pi by 180. Now, sin 8 pi by 180 is 0.139. So, 200 into 9.81 multiplied by 0.139, and this goes to 273 Newton. Look at this. What does it tell you? For a two-wheeler at 30 kilometer per hour, drag is small. Rolling resistance is slightly higher, but if you have your 8 degree slope, the main force that you need to overcome is a climbing force. Remember, with 8 degree slope you will go up, sometime you will climb down. When you climb down, you will actually recover this, the force required will be negative of this. So, in some sense it is possible for you to recover that energy. Of course, you cannot recover it 100%, but in electric vehicle you can recover energy. While you are going down, you can convert that energy going down, the deceleration part or climbing down part, back to electrical energy and push it into the battery. We will discuss with this later, but this was just a simple calculation that I wanted you to do, and for you to get familiar. This question is a much bigger question. It has 3 vehicles, not 1. I did it only for 1 vehicle. For the other 2 vehicles, you please solve. So, now I am ready to say what is the total traction force. Vehicle needs a traction power applied for it to move and accelerate. So, traction power has to be minimum a sum of the 3 powers, the aerodynamic resistance, rolling resistance and climbing force, if there is any climb. That will just be enough to keep it moving, and if I want to accelerate, I will need more power. So, traction power in internal combustion engine actually comes from a petrol and diesel engine. For electric vehicles, it will come through motor and controllers. So, in some sense I am actually determining what is the kind of power that I require for my motors and controllers. So, the traction force creates a force called F track on the vehicle to move forward. Now, this is the force. What about the velocity? What about the power? The power is traction force multiplied by velocity. Power is force into velocity. So, we have to actually calculate the traction power, not traction force is not enough. We have to multiply it by the velocity, and that gives an important result, and we will come to that. Similarly, there is one more parameter which is extremely important other than the power. What is the torque required? Torque required is also dependent on the force, but it is force into the wheel radius. The torque is force into wheel radius. So, we will have to actually compute the power requirement and the torque requirement. These will be 2 fundamental things, and they are independent. Remember, while both of them are dependent on traction force, one of them is traction force multiplied by velocity, another is traction force multiplied by the wheel radius. So, actually torque is always proportional to the force alone. whereas traction power is proportional to both the force as well as the velocity, wheel radius being a constant. Okay. So, this is what we have to actually worry about. So, we will learn throughout the course that traction and speed, and by the way speed for a motor is referred to in RPM, revolutions per meter, no minute, revolutions per minute, revolutions per minute. So, that is how the speed is referred to, while the speed in the units that we will refer to is meter per second, but for the motor it is revolutions per minute, and we will need to convert revolutions per minute into the meter per second are the two fundamental parameter, torque and speed. In fact, motor is always designed for certain torque speed characteristics. So, are the fundamental parameters of either a motor or a engine, and a vehicle RPM is related to the velocity. How is it related? Revolutions per minute. So, RPM multiplied by 2 pi into radius of the wheel. This will give me the total meters that I travel, but this will give me meters per minute. Now, to get meters per second I have to divide it by 60. So, velocity is RPM into 2 pi R wheel divided by 60. What about traction force? Traction force I have already said it is acceleration force. I have not defined the acceleration force, but all of us know that the acceleration force is ma plus aerodynamic resistance plus rolling resistance plus climbing force, and this is the aerodynamic resistance plus aerodynamic drag plus rolling resistance plus climbing force, where A is the acceleration in dV by dt. This will give me the traction force. Once I know my traction force, I can know the power, because power is traction force multiplied by the velocity. This of course, by the way also include the acceleration. What the acceleration is we do not know yet. How do we compute another very fundamental parameter called energy? It is the total power integrated over time. Different amount of power may be required for the vehicle at different time. Why different power may be required? Because sometimes the vehicle may be moving faster, sometimes it may be moving slower, sometimes it may be moving up the slope. So, we will have to compute the power at every instant and integrate the power over time, and this will give me in watt second the total energy. Power I will get in watts and energy I will get in watt second, and this watt second will then can be converted into watt hour and kilowatt hour by dividing. It is actually watt second can be converted to kilowatt hour by dividing it by 3.6. Why? Because 1000 watt, a kilowatt is 1000 watt, hour is 3600 seconds. So, if I divide it by 3.6, I will get kilowatt hour. So, this will give me energy. Energy will always be in watt second or watt hour or kilowatt hour. Force will be in newtons, power will be in watts, and speed will either be in RPM or meter per second. These are the parameters of extreme importance. And finally, the torque, I forgot the torque. Torque is in newtons multiplied by meter, because it is the force multiplied by the wheel radius. So, these are the 5 fundamental parameters that I have to always worry. This is so far what I have done is common to a internal combustion engine vehicle and a electric vehicle. But here the first difference will come. When I talk about electric vehicle, the electric vehicle will have something called regeneration. What is regeneration? Suppose vehicle is moving at a certain speed and you are applying brake to decelerate. In a normal vehicle, in a petrol vehicle, when you decelerate, you apply a brake, what happens? That it was moving at a certain velocity, so it had a certain kinetic energy. Now, this kinetic energy will be lost as heat. The brake will produce heat and it will be lost as heat. That much energy is lost. You can't do much about it. We will later on show you, not so in electric vehicle. It is electric motor which is being driven to take the vehicle forward. When I want to decelerate, I do not necessarily apply a brake which is a friction force against the rotor to stop it, but actually I try to start applying a force on the motor, a reverse force to reverse it, to slow it down, and I can do it electrically. Now, when I do that, when I try to slow down an electric motor, just like I give a electrical power to get the motor to move, when I want to slow it down, it will convert it back into electrical power, electrical energy. That electrical energy actually can be fed back to the battery. So, braking is not all loss. Theoretically, you can design something which can recover all the braking energy back into electrical energy and put it into the vehicle. If the regeneration, so there is a concept called regeneration efficiency. Regeneration efficiency is when you convert it back, what is the loss percentage, loss ratio. If the regeneration efficiency is 1, it means there is no loss at all. If the regeneration efficiency is 0.8, that means 20% is lost, 80% you are able to, if regeneration factor is 80%, you are able to get it. But in reality, of course, regeneration efficiency is much smaller, more like 15 to 30%, in which case the you only get back 15 to 30%. But just imagine a situation where I can get back 100% of the energy back, which means I accelerate in a vehicle, When I accelerate a vehicle, I will consume certain energy, then I will go at a flat speed, I will not consume any, I will consume only a limited amount of energy, no acceleration energy is required, then I will decelerate. Finally, suppose I am accelerating from 0 to 60 km per hour, finally some point of time I have to decelerate from back to 0. So, my acceleration and deceleration may completely cancel out. Now, if I can recover all the energy, whatever energy I put for acceleration, same amount of energy I can get back during deceleration. That will depend on regeneration factor. If regeneration factor is 100%, I can do that. In reality, it is not so, it is actually less, more like 15 to 30%. So, actually I will lose rest of the, suppose it is 30%, that means 70% of energy I will actually lose, only 30% I will recover. So, a regeneration factor R is applied, the net energy used during acceleration and deceleration is R into the energy that was used for acceleration and deceleration. This is important, as we will see. This is only for acceleration and deceleration, it is also for climbing and climb down. During climbing up, you will gain potential energy, your electrical energy is going to convert it into potential energy. Climbing down, that potential energy can be converted back to electrical energy. And if the R factor was if the regeneration factor was 100%, actually for my climbing and climbing down, I consume no energy. But if it is 30%, I actually will consume 70% of the energy. So, a very important factor that you must remember, that the net energy consumed is R into the energy that we had just computed earlier, and R is the regeneration, the regeneration, and R is the equal to 1 minus regeneration factor, because if 15 to 30% only I can recover, 85 to 70% is what I will lose, and that is what we are trying to do. Is that clear? This is for electric vehicle, this is not so for ICE vehicle. Though today many of the petrol vehicles have a certain amount of regeneration. Sometimes they call it even a mild hybrid, and there is normally always a battery, and they will try to recharge the battery. So, to that extent they will recover the energy, it is possible to do that, but with electric vehicle this is going to become more and more prominent. Over time we will learn to increase the regeneration factor from today's number of 20% to 30% to 50%, 60%, 70%, and tomorrow it may be that the climbing up or acceleration does not consume much electricity, but going flat, what is the energy that you will consume? The aerodynamics and rolling resistance, whatever that energy I will always consume. The climbing and acceleration will disappear. So, this is something that you should keep in mind when we talk about the electric vehicles.